In this video, we're going to use related rates to solve problems involving volume. A tank is shaped like an upside down square pyramid with base 3 meters by 3 meters and a height of 7 meters, as shown in the figure below. How fast does the height increase when the water is 3 meters deep if water is being pumped in at a rate of 0.7 meters cubed per second? So first of all, let's write down what the volume of a square cube is. The volume of a square cube is equal to 1/3 s squared h, where s is the, we're going to call that, because this is a square, this would be, s would be here, and s would be here. That's the width and the height. So that's the volume for the equation. Now they tell us that water's being pumped in, so that's a volume being pumped in, so we're adding in some volume, and we're going to write that as dV over dt, because that's a rate, is 0.7 meters cubed per second. They also tell us that how fast does the height increase when the water is 3 meters deep. So they tell us that height is equal to 3 meters. Height of the water is equal to 3 meters, but that's not constant. That's at one specific moment. So what we want to figure out is a ratio between the height and basically the base of this thing. So to figure out this ratio, what we want to do is we want to say that, let's see, we can say that the S value of this thing, so S value here, would be 3/7 of the height. Let's think about that for a second. Whatever my height is, which in this case is 7, if I plug 7 in here, take it times 3/7, I get S. Well, that's true for us there. So if we take 7 and we plug it in here, we'd get S. So the reason I'm using this ratio between the base and the height is because when we want to take the derivative of this equation, we'd really like to take the derivative of this equation with respect to just with respect to time, but of one variable. We don't want two variables in here. So we want to actually replace either S or H with this ratio here. Now, what do they ask us for? They say, how fast does the height increase? Okay, so they're asking us for dH over dt. So that tells us what we need to do here. If they're asking us for dH over dt, we need to solve this equation for S and then substitute it in here for S here so that we can actually take the derivative. So let's start by doing V equals 1/3, and we'll say that this is 3/7 H squared times H. So we have volume is 1/3. If we take 3/7 and we square that, we get 9 over 49. So we have 9 over 49 H squared times H. We can now simplify that to, if we multiply that times 1/3, we cross cancel here, we get 1 over 49 H cubed. So we now have an equation for the volume with respect to the height, and we used the side length, S, substitution there to get to this part right here. Now we want to take the derivative of this with respect to time. And when we do that, we end up with dV over dt is equal to, if we take the derivative of this piece here, the 3 would come to the front, and we get 3 over 49 H squared. But we're taking the derivative of H with respect to t, so that's dH over dt. So that's actually what we're trying to find, is dH over dt here. Now they give us the height already, and they give us dV over dt. So we can go ahead and plug in dV over dt. That's 0.7 meters cubed per second. And we can plug in the height. We would have 3 over 49 times, if we plug in 7, right, the height was 3 meters. 3 meters squared dH over dt. So let's go ahead and evaluate this. So we're going to say that this is 0.7 meters cubed per second. And we're going to divide, or actually multiply this. So that'd be 3 cubed, which is 27, over 49 meters squared dH over dt. We'll divide that across. And so we end up with dH over dt. It's going to equal, I'm going to take 0.7 and divide it by this fraction, 27 over 49. And I get 1.27, so that's 1.27 meters per second. So this should be the rate that the height is changing. So it's moving up pretty quickly there.